So good morning. So slides, are the slides visible?
Yes, sir.
Yeah. What about the other students? Diana and I think they have not joined. Yeah, we'll wait for another 2 minutes, then we'll start. Bhumika has joined,
Yes, sir.
Nitish Kumar, yeah, there. One more Diana has to join. So are the slides visible?
Yes, sir.
Yes, sir.
Fine. So let me start. Fine. So last what we had dealt is regarding the second order effects. So in the module 1, they may ask you to explain some of the second order effects or non-ideal effects, so which are common in a MOS device, or they may specifically ask to explain the body effect or explain the mobility variation or explain the drain punch through effect. Okay, so like that they may ask, or they may ask you to list out all the second order effects or non-ideal effects, so which are there in the short channel. So not to forget, all the second order effects are typically there in the short channel devices. So we have seen the we have seen the velocity saturation. So for that we have this particular figure. So where the drift velocity is being saturated. So once we cross this critical field, so as a whole, you can remember some equations regarding each and every concept along with the figures related. That will be more than enough. We had seen the mobility degradation. We have seen the drain punch through. And last, we were discussing the body effect. So this body effect will cause us the change in the threshold voltage of the MOSFET. So because of the difference in the voltage between the substrate or the body and the source terminal. So because of the variation of voltage between the body and the source terminal, we have the variation in the threshold voltage, and that we call it as body effect. So like if you are having a problem in understanding all the equations, so then what you can do is, so you can define the body effect, and last equation is this one. Okay, so the equation for threshold voltage is this one, and this equation indicates that we have increase in the body effect with respect to the VTO. So can you remember this particular equation for body effect, as well as we do have so one figure for it. Here we have the figure for explanation of body effect. And this is the normal figure like what we have seen while we are discussing the operation of a MOS device, accumulation, inversion, and depletion operations. So we have here the source terminal, and we have here the drain terminal and the gate terminal. Along with that, this SiO2 layer is acting as insulator layer between the gate and the channel, and we have the polysilicon material. So from that, like I'll be taking the gate terminal. So like except the small changes. So this substrate, okay, so this substrate or the body is been represented using a P plus well, okay, like as this substrate is of P type material, so this same substrate is been represented using a P plus well, and this we call it as VB. What is VB? VB is the substrate voltage or the body voltage or the bulk potential. Okay, so here the source has been given for the ground potential, and VG is given a positive voltage at the gate. Okay, so here source and drain terminal. So this source and drain terminal are reverse biased. Why? Because so this source and drain are being connected to N plus. So the source terminal and the drain terminal are reverse biased as they connected to the N plus region. Here it is. Okay, so the first statement. Second point is so the bulk terminal or the substrate or the body potential is also important. and this is in the reverse bias condition. Okay, why? Because so this so-called the bulk is given for the most negative potential, that is the ground terminal. So what we need to understand here is generally the source terminal, okay, so the source terminal and the bulk terminal or the substrate of the body needs to be at the same potential. Suppose if I have this condition where VB, so this so-called bulk voltage is less than the source voltage. Okay, why? Because here this P plus region is more reverse bias than it was before. Okay, suppose if I have this bulk potential to be less than the source potential, so what this effect is, so like this will affect the attraction of more holes of substrate towards it. So this point, as the bulk voltage is less than the source voltage, it will attract more holes of substrate towards it. So this particular statement is being shown using these arrow mark. As this bulk voltage or this P plus region is connected, I mean it has been less than the source voltage. So because of this, so whatever the holes that were there in the P plus substrate will be attracted towards the P plus region. So as these holes move, they will leave negative ions in the substrate. So as we have the displacement of holes from this part of the device to the bulk or is P plus well, so we have the creation of negative ions in the substrate. So but already we have negative ions in the channel. Here they are. Okay, as it is a NMOS device in the channel, what we expect is the electrons to be flowing. Okay, right, like already we have electrons in the channel, and here as this base, as this bulk voltage is less than the source voltage, so we have here the attraction of holes like that are present in the substrate to the P plus well. Hence this will in turn have the creation of more negative ions. So but already we have here negative ions in the channel. So now as negative ions are more in the substrate, we need to compensate this with increasing Vg. Why? Because so whatever the number of electrons are there, okay, same number of electrons should be actually compensated with same number of holes at the gate terminal. Okay, hence what we can do is I can increase the gate voltage. Okay, so this like, so what we're having the increase in the gate voltage, so as to compensate for equal number of electrons in the channel, we call it as mirroring. Okay, means the positive charge on the gate, okay, should be equal to negative charge in the channel. Okay, so here like the main cause for increase of this gate voltage, why we should increase the gate voltage is because we have here the more number of electrons are there in the channel. Hence to compensate that, I need to increase the gate voltage so as to have more and more accumulation of positive charge. Hence here we are not changing the Vg intentionally. Okay, so here is gate voltage is not being increased intentionally, but here as we have the movement of holes from the substrate to the P plus region, like here we have more ions to be deposited, and already we have the negative ions in the channel. So due to this, we have more and more number of negative ions. Okay, so to compensate this more number of negative ions in the channel, I need to have more and more deposition of positive charges on the gate terminal. So to achieve this, I need to increase the gate voltage. Okay, so this increase of gate voltage, what we need to achieve is called as body effect. Okay, right. So the second, so the next non-ideal effect is subthreshold conduction. So this word subthreshold conduction is indicating like this particular area, say from 0 to VT. Again, this VT, what is VT? VT is the threshold voltage that needs to be applied at the gate terminal so as to turn on the device. Like we have seen this in the earlier slides as well. So this VT is nothing but the threshold voltage of the device. Okay. So that needs to be applied at the gate terminal so as to turn on the device and to make the current to be flowing in the channel. Okay. So the next non-ideal effect, we call it as a subthreshold conduction. Okay, so we have here subthreshold conduction as the heading, and this is the next non-ideal effect. So we know that if this VGS is greater than VT, suppose if the input voltage or the gate voltage is greater than the threshold voltage of the device, so then the device will be conducting and you can expect the flow of current. So, but even before VT is reached, so but suppose if the voltage is less than VT also, okay, so still we can expect the flow of current from drain to source. Here we have this. Okay, so we have this small flow of current, even though the threshold voltage is not been reached. Okay, so when VGS is less than VT, okay, so the current inside the channel does not reduce to zero. Okay, so what we expect ideally is, suppose if this threshold voltage is not being achieved, so then I should expect absolutely zero current to be flowing the channel. So but that will not be the case. Okay, even though we have not increased the voltage so as to exceed the threshold voltage, even then I can expect a small flow of current that is flowing inside the channel. Means the current is not equal to absolutely zero. Okay, so we have a finite flow of current here, and you can also make use of this expression ID in the subthreshold region, where I know where ID is equal to I naught raised to the power of VGS by eta into VT, where this eta is non-ideal factor, and that is greater than equal to that is greater than so this factor, this eta is non-ideal factor and is always greater than 1. So you can take the help of this particular figure where we are showing that even though we have not applied enough voltage so as to turn on the device, but still we have a finite flow of current. Okay, so the current ID is not exactly equal to zero, so but still you can have some small flow of current. Okay, so we know that increase in the VGS value or the voltage that gets applied at the gate, we get a lot of current. Okay, so we know that like in case of MOS device, so by applying the voltage at the gate, and as and how I increase the gate voltage, I will achieve more flow of ID, right, or the gate current. So but like we should be more careful here. Why? Because even though I can achieve more amount of drain current as and how I increase the gate voltage, so but if I say just keep on increasing the gate voltage, so then what will happen is the oxide layer, okay, so like the oxide layer or the SiO2 layer that is right below the gate will break down. Okay, hence the device can go into damage. Okay, hence we should have appreciable application of the gate voltage so as to have enough gate current. Okay, so we can explain this subthreshold conduction using this particular small graph. Okay, so next is so called the tunneling effect. Okay, so this can be simply called as the tunneling effect or more correctly Fowler-Nordin tunneling. Okay, so what is the concept regarding this is even though it is assumed that IGS is equal to 0, okay, a small IG will flow when gate oxide is very thin. Okay, like even though we have this a very thin layer of SiO2 is there, okay, and this will act as insulator. So but still we have a very small flow of current. Okay, a small gate current will be able to flow, like even though the gates of the gate oxide layer is very thin. So this current is due to the electron tunneling. Okay, and this is proportional to the area of the gate. Okay, Suppose if the area of the gate is larger, then this tunneling current will be also large. Okay, so this effect we call it as a Fowler-Nordin tunneling, and we have expression for this effect as well, where IFN or the Fowler-Nordin current IFN is given by C1 W into L E of square into E into minus E naught by Eox, where Eox is given by VGS by Tox, and E naught and C1 are constant. So we have a limitation on the thickness of the gate oxide as the process are scaled down. So what do you mean by this is like due to the advancement in technologies, we have the smaller and smaller devices. Hence, the gate oxide thickness is also reducing. So, but I cannot have the least value of the thickness of gate oxide or SiO2 layer. So we do have a limitation on the thickness of the gate oxide. So one such effect we call it as oxide breakdown. Okay, so the biggest problem. What we face is the oxide breakdown or the thickness of gate oxide. Or the oxide layer can go to the damaging level. Why? Because of the application of a high amount of electric field, which will cause this SiO2 layer to go into breakdown or damage, and we can have the conduction of the current. Like exactly similar example is seen in the lightning application, like thunderstorm lightning effect. So like even though the air is insulator, so but still, so when lightning happens, okay, where we have a high amount of electric field is caused, and that field can pass through the air, right? So basically that air is insulator. So but due to the high application of electric field, where that air will be breaking down, and we have the flow of current. Okay, like exactly same thing uh, like will happen in the lightning effect, like due to heavy rains and storms. So you can expect this lightning to be happening. So where due to the high amount of electric field, the insulator, I mean air, which is actually an insulator, will break down, and we can have the flow of current. So we can also take the help of this particular equation where we're calculating the breakdown voltage. Okay, so upon what amount of voltage I can expect this oxide layer to be breaking down. So for SiO2, the breakdown electric field is 6 into 10 to the power of 6 volt per centimeter. And if the thickness of the oxide layer, so called TOX, is 50 nanometer, so then I can calculate the breakdown voltage for this 50 nanometer of gate oxide. So the equation to calculate the breakdown voltage is V breakdown is equal to E breakdown or the electric field value, so as to obtain the breakdown, into the thickness of oxide layer. And here E breakdown voltage is 6 into 10 to the power of 6, and the thickness of gate oxide layer is 50 nanometer. Hence the breakdown voltage at which you can expect the oxide layer to be breaking down is 30 volts. Okay, so what is the basic concept here is, due to the heavy amount of electric field in the MOS transistor, the gate oxide layer can break down. Okay, even though the gate oxide layer is insulator, so but still it can break down, and we can have the current to be conducting. Okay, so next non-ideal effect is the channel length modulation, and that is the like we represented using this symbol called as lambda. So we have here channel length modulation as the next non-ideal effect. Okay, and this figure is like well known to you, like in the saturation region. So we have the effect of this reduction in the channel length. Like earlier we had this much as the channel length. So but due to the increase in the VDS value or drain to source voltage. Okay, here it is, like due to the increase in the the drain voltage or the drain to source voltage. Okay, so we have here the reduction in the channel length, like as shown by this particular line. Okay, like earlier the length of channel was from this end to this end, and due to the increase of the drain voltage, okay, by sourcing the ground terminal, suppose if I increase the drain voltage, so then the channel length is being reduced, and this effect is also called as pinch off effect, where we have the reduction in the channel length. So here to explain this channel length modulation, suppose if I have the increase of the drain voltage, by grounding the source potential to 0 volts, we have the channel length to be reduced. Okay, so we have the channel length to be reduced, and this effect is called as channel length modulation. Okay, so till now, so what we have discussed is all these non-ideal effects, and all the effects will be supported by some definitions, some equations, as well as say some figures like this. Say from examination point of view, you remember all these non-ideal effects and whatever the effects that are being discussed in the slides. Okay, and you can support this by using some figures, equations, and some select graphs, etc. Okay, so next is this CMOS inverter. So we have this CMOS inverter where we have a combination of so this NMOS, NMOS and PMOS, and we have this like VI curves for this CMOS inverter. Like explain the DC characteristic curves of a CMOS inverter. Like this can be the question, and we have a small graph for this, like having 5 regions. Here it is. So we have a simple graph like this. Like this we call it as a DC transfer characteristics of inverter. Again, we have here V in on x-axis and V out along the y-axis. And this particular DC transfer characteristic curve or DC curve of a MOS inverter will be having in total 5 regions. Now this is region 1, this is region 2, region 3, region 4 is here, and region 5 is here. Okay, so that we have here to analyze the operation of this CMOS inverter, like having NMOS and PMOS devices. So by the application of V is equal to 0 and V is greater than equal to 1 and V is equal to V0 and V is greater than equal to 2.5 volts, etc. So by application of different voltages at the input of the inverter, like we'll be seeing the output voltage obtained at the output terminal, as well as we do analyze the various regions of operations of both the devices PMOS and NMOS. Okay, how these device PMOS and NMOS will be behaving for the different value of input voltages applied for the inverter. So for example, select first I'll keep this V is equal to 0 and then I'll increase this to 1 volts. Okay, and still further increase this to select V is equal to 5 volts. So upon the increase of V in voltage, say from 0 to 5 volts in different values, okay, so what is the amount of output voltage obtained, as well as how these NMOS and PMOS devices will behave, or in which region of operation does this NMOS and PMOS devices will be operating. And as we know that like in case of operation of MOS device, okay, we have basically 3 regions of operation, and those are cutoff region, and then linear region and saturation region. Okay, so the bottom line is this table is very much important. Okay, this table is very much important, and based upon this table only, this particular DC characteristic curves is drawn. Okay, so where the V voltage is being varied along the x-axis. Okay, and we can have the output to be plotting on the y-axis, and this is the curve obtained. Okay, so to arrive at this, let me start with the first slide. Right, so like here is here is the CMOS inverter circuit, right? And this circuit was being discussed in the offline class. Is it right, participants?
Yes, sir.
So the CMOS inverter offline class ಅಲ್ಲಿ ಕೂಡ lab ಅಲ್ಲಿ discuss ಮಾಡಿತ್ತಲ್ವಾ? So we have
Yes,
this
sir.
same diagram. So we have this PMOS device as the pull-up device, and the NMOS device is acting as a pull-down device. Okay, so we can have the shorting of the gate and gate of both the devices, and always the source of PMOS should be going for VDD, and the source of NMOS should be going for the ground. So for this particular circuit, the highest potential is VDD and the lowest potential is what? Ground. Right? Are you seeing this?
Yes, sir.
Bhumika 17EC006.
Yes, sir.
So we have this circuit of CMOS inverter. So we have the pull-up devices PMOS and pull-down device NMOS. Okay. So for this particular circuit, this VIN is applied for the gate. So for the common gate of NMOS and PMOS, and at the point of at the drain of both the devices, I can take out the output point. So for this particular whole circuit, like this has got single input and single output. So here the application of voltage or the voltage difference between the different terminals is much more important. Okay, so here the like the basic concept is like I'll be applying the input voltage, say from from 0 to 5 volts. Okay, so like 0 and 1 volt and 1.5 volt and 2.5 volts up to 5 volts. Suppose if I go on increasing the VIN voltage, how these PMOS and NMOS device will behave, or in what all regions we have the operations of the PMOS and NMOS upon the increase of VIN voltage within the range of 0 to 5 volts. So that needs to be analyzed. Okay, and we know that exactly at VDD by 2. Suppose if I take this VDD as 5 volts, right? Exactly at 5 divided by 2 is equal to 2.5 volts. We have the switching of this inverter. Okay, so like this can be seen here. Suppose if I look at the graph, yeah, here it is. So this VIN is equal to V out at exactly 2.5 volts, and in the region number 3 we have the transition from, say, from high to low. Okay, so we have this VDD by 2 region. On the third region, we can expect VIN to be equal to V out, where both the devices, this NMOS and PMOS, both will be operating in the saturation region, and this we call it as the transition region of the inverter, and this will happen exactly at VDD by 2. And if I take VDD is equal to 5 volts, 5 divided by 2 is equal to exactly 2.5 volts. You have both the devices NMOS and PMOS will be able to operate in saturation region, where we have a direct contact between the PMOS and the NMOS, means both these devices. So both NMOS, say both this NMOS and PMOS will be on, hence we have a direct contact between the high potential and the low potential. Suppose if these two devices are on, means these two devices will be offering low resistance, hence we have a direct contact between high potential and low potential, and current can easily flow through it. Okay, yeah. So we have the nature of the DC curves of a CMOS inverter along with the circuit. Circuit is as shown here, and we have represented different voltage. Okay, so for example, VGS comma P is gate to source voltage of the PMOS device, and this is between the gate and the source terminal. And remember that always the source of PMOS should be going for VDD, and the source of NMOS should be going for the ground. Okay, yeah, same figure it is. So we have VGS comma P. Similarly, VDS comma P. VDS comma P is nothing but the potential or the voltage difference between the drain and the source, and this comma P indicates this VDS is for the PMOS device. Similarly, for NMOS device, we have VGS comma N. VGS is nothing but the input voltage that gets applied between the gate and the source of NMOS device, and the VDSN is the drain to source voltage of this NMOS device. Okay. Similarly, we have VDS comma P, where VDS comma P is voltage difference between the drain and the source of the PMOS device. Okay. Yeah. So we have to understand these equations. Okay. So let me start with the basic details. So we have so just 10 minutes remaining. Let me have a brief introduction regarding these equations, and we'll deal with the next equation in the next class. Okay, so first, from examination point of view, let me have a discussion. So from examination point of view, you need to draw the CMOS inverter circuit having the PMOS and NMOS devices. Do remember that this PMOS is on if this gate voltage is 0. Similarly, NMOS is on if this gate voltage is applied with the high value, means logical high or equal to plus 5 volts. Okay. So for this particular whole circuit, let me assume this VDD is equal to 5 volt, here it is, and VSS is equal to 0 volts, here it is, and VGSN is equal to Vin. Why? Because say for NMOS device, okay, so for NMOS device, if you see, means VGSN is right here, where the gate is applied with the input voltage by grounding the source terminal. Hence, VGS is this potential for NMOS device, that is equal to Vin. Similarly, VDS comma N, VDS comma N is this particular voltage, and the VDSN is equal to V out. Similarly, for this VGS comma P, right? So this VGS comma P is right here, right? As I'm indicating right now, okay? So this VGSN comma P is nothing but high potential minus low potential, where this source has been given to VDD, hence it is VDD minus VIN. Okay, so but the standard notation what we must use is VSG. So why it is VSG, why not VGS? Okay, normally we tell it as VGS comma P. So but the standard notation what you are supposed to use is VSG, where VSG is VS minus VG. So why it is VS minus VG? Why not VG minus VS is? Why? Because when compared to the gate, this source is at the high potential, hence it should be VS minus VG. Okay. So like suppose if I'm using standard notation, so then VSG is given by VS minus VG, where VS is equal to VDD. See here, VS is equal to VDD, and VG, what is VG? VG of this PMOS is given for V internal. So hence VS is equal to VDD and VG is Vin. So but yeah, so but as we are using here VGS instead of VSG, hence VSG is equal to minus VSG, hence we get VGS of P is equal to minus of VDD minus Vin. Okay. Similarly, like if I take this VDS of P devices, here it is, VDS of P devices, the standard notation should be VSD comma P. Why? Because again the source of PMOS is at high potential when compared to the drain, hence always VDSP should be called as VSD comma P, where VSD is VS minus VD, and here VH is this source voltage of PMOS, here it is going for VDD, here it is, and VD is the drain voltage, and that is going for V out. Okay, hence I can write VDS comma P as minus VDD minus V out, means VDD minus V out whole, so this whole term is minus. Okay, so by keeping these equations in mind, okay, like at the end, right? So once we deal with all these equations where we are keep on varying the input voltage, say from 0 volts to say 1 volt and 2.5 volts and 5 volts. Now, within the range of 0 to 5 volts, if I keep on reading the Vin voltage, okay, I can be calculating the output voltage. Also, I will be examining in what all regions I have the operation of NMOS and PMOS. Okay, so for that, I mean, like after discussion of all these equations, so what we need to remember is only this, where our NMOS is in off condition when Vin is less than the threshold voltage of NMOS device, and my NMOS will be in the linear region of operation if this VGS parameter or Vin is greater than VTN and Vout. So for this NMOS device, Vout is equal to VDS, right? So if this VDS is less than VGS minus VTN, and note that this VGS minus VTN we call it as effective voltage. So suppose if this VDS is less than the effective voltage, then my NMOS will be in the linear region. And if this Vin is less than the threshold voltage of NMOS device, my NMOS device will be in the off region. I mean, so-called cutoff region. Similarly, for the PMOS device, my PMOS device will be in the off condition if VGSP is greater than VTP. Okay, so what is VGSP? This term is been rightly shown here. Okay, so this VGSP. So if the PMOS device has its VGSP greater than VTP, where this VGSP is nothing but VG minus VS, where VG is Vin and VS is VDD. So this whole term is nothing but VGSP is greater than VTP, or I can write in terms of Vin brother. So then we will be in terms of Vin is greater than VDD plus VTP. Suppose if this Vin is greater than VDD plus VTP, then my PMOS will be in the off region. Similarly, my PMOS will be in the linear region, right? If this Vin is less than VDD minus VTP, okay. And second condition, if this VDSP is greater than VGSP minus VTP, where VDSP is VD minus VS, where VD is Vout and VS is VDD, is greater than, again this term VGSP is equal to VG minus VS, where VG is Vin and VS is VDD, and this same term minus VTP is shown here. So this VDD get cancelled, hence Vout is greater than Vin minus VTP. So for this particular condition, my PMOS will be in the linear region. Okay. So by keeping the bottom line of all these equations is this equation. Okay. Yeah. So for the first case, like let me assume this Vin is equal to 1 volt. Suppose if Vin is equal to 1 volt, and if I have this VTP. So what is VTP? VTP is the threshold voltage of PMOS device. And we know that always threshold voltage for this PMOS will be in terms of negative value. Okay. So suppose this VTP is equal to minus 1 volt for PMOS device and Vin is equal to 1 volt. So for the case 1, okay. So let me have this, it is VTN it is. Okay, so this VTN is the threshold voltage of NMOS device and VTP is a threshold voltage for PMOS. And we know that the threshold voltage for NMOS is positive and the threshold voltage for PMOS will be negative. So for the first case, so what we are assuming here is, suppose if this Vin is equal to 0, and obviously according to the function of inverter, so what inverter does, if input is equal to 0 means output will be equal to high. Okay, same thing it is. If Vin is equal to 0 volts, then what we expect is V0 is equal to 5 volts. So by considering this VT is equal to 1 volt and VTP is equal to minus 1 volts for this NMOS and PMOS devices. So now let us check the devices, how this device PMOS and NMOS will behave. So like if we see this NMOS device or the pull down device, here it is. So for its pull down device, the input voltage is VGSN and output voltage is VDS, okay. So for NMOS, this VGSN is equal to Vin, that is equal to 0, right? And this 0 voltage is less than VTN, where VTN is equal to 1 volts and input voltage is being 0 volt. Hence, 0 volts is less than 1 volt. Hence, this NMOS will be in the cutoff region. Okay. And if you see the PMOS device means VGSN, P is given by VDD minus VTN whole minus. So here is so-called VG. What is the value of VDD? Is 5 volts, and V is equal to 0 volts. Hence 5 minus 0 is 5, and it is minus 5 volts. Okay. So here, given the value of VTP, like in terms of minus value, minus 1 volt, if this VGS comma P is less than the threshold voltage of the PMOS device, okay, so then my device is on. So my PMOS is on